The universe is governed by the relentless laws of thermodynamics. The supply of energy is finite, meaning that eventually, the cosmos will exhaust its fuel and every point of light will permanently extinguish. We currently exist in what astrophysicists call the Stelliferous Era. It is a vibrant, energetic period of cosmic history, where galaxies are illuminated by billions of active stars. But the supply of interstellar gas required to forge those stars is limited, and it is actively being depleted as you watch this. Once that material is gone, star formation will completely cease. The lights of the universe will begin to blink out, one by one, leaving galaxies to cool in the dark. To understand the ultimate fate of our cosmos, we have to travel trillions of years into the future to find the very last star to shine in the universe. By tracing the life and death of this final survivor, scientists can piece together the long-term thermodynamic evolution of the universe and the ultimate destiny of all baryonic matter. The universe today is 13.8 billion years old. That scale is difficult to grasp, but on a cosmic timeline, it is only the earliest morning. This timeline charts the cosmos's far future. In 10 billion years, sun-like stars exhaust their fuel and die. By 1 trillion years, galaxies merge. By 10 trillion years, free gas is totally exhausted, bringing star formation to a definitive end. The stars that remain will be the lowest mass red dwarfs, specifically those born with the absolute minimum mass required to ignite nuclear fusion, weighing in at roughly 0.08 solar masses. Because the universe is only 13.8 billion years old, no low-mass red dwarf has ever died. Every single one ever born is still shining today. In a universe currently dominated by massive, brilliant giants, the smallest and dimmest objects possess the perfect physical traits to outlast everything else by a factor of 1,000. A low-mass star has significantly less gravitational weight crushing its core. This results in far lower core temperatures, which forces the fusion of hydrogen protons to proceed at a microscopic, highly restrained rate. This visual compares the energy expenditure of the two stars. By the rules of the mass-luminosity relation, a red dwarf with 1/10 the mass of our Sun does not output 1/10 of the light. It outputs roughly 1/3000th of the light. Furthermore, Sun-like stars are highly inefficient. Their cores are surrounded by a radiative zone that traps unburned hydrogen in the outer layers. When the core is empty, the Sun will die, leaving nearly 90% of its total hydrogen completely unused. This cross-section illustrates the internal mechanics of a red dwarf. They are fully convective. Plasma continuously circulates from the core to the surface like boiling water, feeding fresh hydrogen into the center and carrying helium ash out. This ensures 100% of the star's hydrogen is burned. That perfect fuel recycling, combined with an extreme economy of energy, allows a red dwarf to burn steadily for up to 14 trillion years. Eventually, even a fully mixed red dwarf runs out of fuel. 100 trillion years in the future, the final star will approach the end of its hydrogen supply. A star this small lacks the mass and gravitational pressure to expand its outer layers into a red giant. Instead, as the core becomes denser with helium ash, the star must increase its overall surface temperature to maintain hydrostatic equilibrium and prevent immediate collapse. As the surface heats up, it changes its color from a faint red to a brilliant blue-white. Physicists call this theoretical phase a blue dwarf. Right before it dies, this final star will become significantly more luminous than it was for the previous 14 trillion years, burning intensely against an entirely dark and lifeless cosmos. When the very last hydrogen atoms fuse, the engine shuts off. Without outward thermal pressure, gravity instantly collapses the star inward. That collapse is halted by electron degeneracy pressure, a quantum mechanical rule dictating that no two electrons can occupy the same state, defined mathematically by physicist Subramanian Chandrasekhar. The blue dwarf is compressed into an Earth-sized helium-white dwarf, a dense remnant emitting no new energy, glowing purely from residual heat. Over quadrillions of years, that remnant will slowly bleed its remaining thermal energy into the vacuum. It will cool into a dark, crystalline black dwarf, marking the beginning of the degenerate era. With the transition to black dwarfs complete, the universe as a habitat for traditional light and baryonic life is permanently over. What happens to those inert black dwarfs depends on mechanisms we have not yet fully resolved, like the expanding force of dark energy, which could either tear them apart or leave them in frozen isolation. The final timeline relies heavily on the theory of proton decay. Deep underground, in facilities like Super Kamiokande, physicists are searching for evidence that protons themselves are unstable. If grand unified theories are correct and protons do decay, even these frozen black dwarfs will eventually evaporate entirely into pure radiation. The 14 trillion-year lifespan of a star seems incomprehensibly vast, but against the full timeline of the cosmos, the Stelliferous Era is just a fleeting spark. We are incredibly fortunate to exist right now, in the star-filled dawn of the universe, before the lights go out.